Okay, hi everyone. My name is Priyal, and I'm a PhD student at St. Mary's University in Halifax. I'm currently in my third year of my PhD, and my supervisor is Jacob Hanley. And this project is focusing on melt inclusions associated with Archean volcanogenic massive sulphide deposits. And I'm basically focusing on finding the constraints on pre-eruptive metal and volatile contents of magmas. This project is also in collaboration with Thomas Monek from Colorado School of Mines and Steve Piercy from Memorial University. So some of the key objectives of my research are to establish that melt inclusion studies that are usually used on typically younger magmatic hydrothermal ore systems can actually be applied to Archean VMS systems. I'm also trying to determine the chemical conditions of melt inclusions to understand how metals are supplied to the VMS deposits. And another part of my project is to examine the spatiotemporal variations of silicate melt chemistry from metal fertile and barren volcanic units to understand the evolutionary history of VMS deposits in the Abitibi. So we're doing this by characterizing the ore metal and volatile chemistry of melt inclusions in zircon, as well as the physiochemical conditions at the time of melt entrapment. This is to compare metal fertile volcanic units to barren volcanic units and predict fertility quantitatively. I would just like to point out that there is currently no published melt inclusion data for Archean rocks, so this is a very novel study. So just to recap on my study areas from last year, I'm focusing on the Kid Creek VMS deposit and the Laron Pena VMS deposit. The reason we chose these two is to identify the differences mainly between gold endowment, as Kid Creek is not very gold rich, whereas Laron Pena is gold rich. And I'll also be looking at different stratigraphic units within these VMS deposits to look at the silicate melt inclusions hosted in pre-Sin and post-VMS or volcanic units. Besides looking at the two metal-rich assemblages in the Abitibi, I'll also be looking at silicate melt inclusions that are hosted in barren volcanic assemblages in the Abitibi that bracket productive assemblages such as the Pico, Deloro, Tisdale, Porcupine, and Temiskaming assemblages. So I collected a large number of archived hand and drill core samples, as well as zircon separates, which were needed for the study. A large number of zircon grains are needed for the study because a lot of the zircons are of bad quality, where you cannot actually identify any melt inclusions. So once I got these the zircons, we sent them for mounting at Boise State University, and some of the zircons were annealed at 900 degrees Celsius, and some of them were left unannealed. I also undertook thin section petrography to identify lithologies containing zircon, as well as to establish the timing of zircon growth relative to other rock forming minerals. And the most important part of my first year was to do melt inclusion petrography for the screening of zircons to see if there's abundant enough of melt inclusions and good quality melt inclusions, and to assess the origin, size, depth, shape preservation in order to do future analytical work. I also did some scanning electron microscopy to look at the inclusion mineralogy, to see if there were daughter and accidentally trapped phases, and also to look at the bulk inclusion composition of exposed melt inclusions in the zircons. Another important method that I'm using is laser ablation inductively coupled plasma mass spectrometry to quantify the major and trace element compositions of melt inclusions, as well as the host zircon chemistry, and to look at mineral chemistry for allied thermobarometry. I'll also be doing cathodoluminescence imaging of the zircons to identify zircon growth domains, for example, xenocrysts, anticrysts, autocrysts. And I'll also be doing some Raman spectroscopy to look at the bulk volatile contents of inclusions. So just to recap on my petrography, we do see a lot of silicate melt inclusions preserved in the zircons. Most of them are, well, some of them are glassy, some of them are recrystallized. There's also other types of inclusions in the zircons, such as apatite, quartz, biotite, and there's also some oxides, such as rutile, magnetite. And we also see some sulphide saturation, meaning we see sulphide inclusions present in the zircon. And we also seen very few cases of sulfides trapped within a silicate melt inclusion. So I have just recently obtained some laser data, and this is just to show that I show the comparison between silicate melt inclusion compositions obtained from the SEM to compositions obtained by LAICPMS. And what I have here is one sample that has been collected from the SEM, and the compositions are quite similar to the compositions of the silicate melt inclusions that were obtained from LAICPMS. And this shows that you can use SEM as a first analysis to have a look at silicate melt inclusions that are exposed on zircon. There's also, as much as the silicate melt inclusions show end member or host lithologies, they also have a big range or a wider range of compositions. And this possibly suggests that the silicate melt inclusions don't only represent host lithologies, but they also represent a variety of evolutions in the VMS system. Again, this is just some melt inclusions plotted on an AFM diagram, and this shows that the silicate melt inclusion compositions show both tholeatic and calc-alkaline compositions, and they do show a large range compared to that of host lithologies. So what I've done, for my first metal data that I have just received, I just plotted these on a box and whisker diagram, and you can see that just by looking at the silicate melt inclusion data, which are the box and whisker figures on the left, you can see variations in the metal concentrations from assemblage to assemblage. The first one shows the metal concentrations for the Kidd-Monroe assemblage, whereas the bottom one shows the metal concentrations for the low row assemblage. And from this, for example, you can see that the low row assemblage has higher copper to zinc ratios compared to that of Kidd-Monroe. And then also comparing those two to whole rock data, you can see that there are slight differences between the ratios, the metal ratios, but there is a widespread of data from the silicate melt inclusions. And this just shows that metal tenures in melt inclusions from different assemblages are distinct. And there's also a range in metal concentrations within single samples. And I just want to point out that these variations are noticed from trapped silicate melt inclusions as opposed to whole rock data. So this diagram is showing the copper, lead, zinc ratios of silicate melt inclusions, and the diagram on the right, on the left, is copper zinc lead ratios of VMS deposits in the Abitibi. And what you can see on the diagram on the right, there is quite an overlap of data from silicate melt inclusions with the VMS deposits in the Abitibi. However, there's also a wider spread of data from the silicate melt inclusions. And again, this may suggest that silicate melt inclusions trap not only the host lithologies, but compositions that show maybe the evolutionary history of VMS deposits. And the silicate melt inclusion compositions on the copper zinc lead ternary also confirm that Abitibi VMS source magmas are zinc dominated, as there is a high number of data points that lie in the zinc corner. So this is a diagram by Otedat and Pitke from 2003 that shows that cesium can be used as a monitor of fractionation. This diagram shows 3 scenarios of crystallization, but all 3 scenarios show that cesium mainly concentrates after 90% of crystallization. And when comparing cesium to metals, we can see that there's very subtle correlation between them. For example, in figure B, you can see that as cesium increases, so does molybdenum. And in the other figures, they are slightly there. But there's also, the data points are also very scattered. So there are other factors that might influence this. For example, okay, so if there's a positive correlation that shows fractionation only, but high values of metals with low cesium values may be due to accidentally trapped sulphides in silicate melt inclusions. For example, in the image on the top right, showing the silicate melt inclusion with chalcopyrite. And in other instances where there's high cesium values with low metal values, this could be fractionation with a loss of metals. And loss of metals could either be due to degassing or a separation of crystallizing sulfides from the magma. Another thing that I'll be looking at for my PhD is the spatiotemporal variations of silicate melt inclusions in zircons. And for this, I'll be using cathodoluminescence imaging to identify different zircon growth domains. For example, xenocrysts, which are in the gray, which are the gray shade, anticrysts, which are the green shade, and autocrysts, which are the red shade. From this image, you can see that most zircons show at least 2 and up to 4 growth zone domains that have distinct luminescence. And silicate melt inclusions are hosted in more than one zircon domain within a single sample. However, we have to use we have to obtain uranium lead ages of each zircon growth zone to see if the zircon growth zones have actually crystallized from different pulses of magma, and if they are coeval with the volcanic host rocks. And then upcoming methods will also be CID terms or SHRM to resolve these zircon xenocryst, anticryst, and autocryst. And these will only be done on representative zircons. And together, this will be tied up with the silicate melt inclusion chemistry to understand when these silicate melt inclusions were trapped and if they show different evolutionary history of the VMS systems. I'll now be handing over to Dr. Jacob Hanley to discuss some host zircon chemistry with you.
Thank you, Priyal. Yeah, just to follow up a little more on what we're doing with the zircon chemistry. This is very preliminary data. It's really just been processed in the last week, so we haven't had a lot of time to digest it. But the advantage, obviously, of doing melt inclusion work in zircons is that you get that added layer of information from the zircon hosts. And what we're seeing is an example. If we just look at some of the samples we've looked at in terms of the overall scatter on trace element diagrams with respect to these parameters that are typically used to identify fractionation trends involving the crystallization of accessory minerals, is that there is quite a large range in the associated zircon host zone compositions. And the goal going forward is going to be aimed at tying those variations in zircon chemistry to the associated melt compositions that Priyal is determining. And again, it's a good supporting evidence that the melt inclusion compositional range we're seeing is really mimicked in the diversity or range in compositions within the associated zircon hosts. And clearly, accessory minerals have had a major impact on the zircon chemistry, even within single samples. Next slide, Priyal. And then if we look at, for example, parameters in this, just one example where you look at rubidium-strontium ratios, which can be used in melt inclusion studies as a proxy for plagioclase crystallization. As we lose plagioclase, we deplete the melt in strontium, and the rubidium and also barium will become enriched until K feldspars start to drop out. If we look at parameters in the melt like that and compare them to rare earth element parameters from the zircon hosts, we start to get the impression that we can use the combination of melt chemistry and zircon chemistry to resolve some of the reasons why there's variation in zircon chem. We know, for example, that europium anomalies in zircon are going to be influenced not only by oxygen fugacity, but also by plagioclase crystallization. And we do see a large number of melt inclusions within growth zones that tend to have the lower europium anomaly values actually having higher overall rubidium-strontium ratios, which would be consistent with those melts having been trapped after the growth of a substantial amount of plagioclase. And that helps to resolve whether variations in the europium anomaly are due to crystal fractionation or oxygen fugacity variations, or both. And again, we see a huge range within single zircon populations within single samples, which is pretty startling. Next slide. And then if we bring in the metal chemistry, this is the same zinc data that Priyal showed from her plots, plotted against cerium anomaly. And as you know, cerium is also a parameter used commonly. Cerium anomaly is also used commonly as a proxy for FO2, but we also know from recent studies by Loader and others that cerium anomalies are very strongly affected by crystal fractionation. And so really that x-axis there is showing you variations likely due to FO2, but also the removal of minerals like titanite and amphibole from the liquids. When we plot those with melt composition, we can see that those Tisdale and Deloro samples with the really high zinc concentrations that are suspected, based on what Priyal showed, to possibly contain some accidentally trapped zinc carriers, perhaps sulphide. Those are associated with the lowest overall cerium anomalies, and therefore magmas that are either at low FO2 or have seen the least removal of things like amphibole, which would remove water, which would obviously allow sulfides to stabilize more readily. So it's very preliminary data, but we're definitely seeing some relationships between different parameters when we're now linking the first melt inclusion chemistry from the laser ablation ICP-MS work to zircon chemistry. We were behind quite a bit. We've lost a full year on Priyal's project because of COVID and other things, but we're on track, and all of the lab work is underway at various stages. The compositional data on the melt inclusions obtained from different methods showing really good internal consistency, which is great. And it's important now that the methods are validated to grow the data set. And we have a major analytical session coming up in late April on melt chemistry following our preliminary session that we did in January. That's some of the data that you see here, where we ironed out various technical challenges. We'll then be doing uranium, lead, and lutetium hafnium work on the inclusion bearing zones within the zircons and reconciling that inclusion data with the entrapment, the timing of entrapment of the melts using cathodoluminescence imaging. And that work will be scheduled for summer and early fall at MUN with Steve and Anne-Sophie and with Bill Davis at the GSC. The plan in the short term is going to have an article, we'll have an article ready for submission this summer, late summer, on the regional assemblages with a focus on that methodology to set some benchmarks for coupled inclusion analysis on Archean rocks. This has never been done before, so it's important that a methodology paper is out. And then we'll have 2 application papers to follow in the coming year or so on the Kidd, Monroe, and Blake River assemblages. I do think the most promising outcome is that we're really seeing differences from assemblage to assemblage, not only in metal endowment, but also state of sulphide saturation and other associated parameters. So it'll be exciting to see what comes out in the next 6 months to a year. Thanks.
Thanks very much, everyone. We have time for a quick question.
I'll ask one if I can, Ross.
Yeah, go ahead.
Yeah, I'm intrigued by the copper lead zinc ratios that were shown in one of the early plots there, and you know those ratios are pretty robust in the ore deposits themselves. How do you account for the pattern that's observed there, especially the high lead? You're muted there.
I'm just looking at the diagram that you were referring to. Can you ask your question again?
Yeah, there was just a big difference between the copper, lead, and zinc ratios between the ore deposits and the inclusions, which seemed odd to me. And the outlier is the lead. So the question is, what's controlling that?
Yeah, so we think that melt inclusions, they don't only trap the host, the composition of the host lithologies, they probably show a more wider range in compositions because they were maybe they were trapped at different times in the VMS system. So the difference in lead, the difference in lead ratios may be due to where if the magmas were leached from rocks, they were probably leached from different areas, or depending on the lead concentrations in the magma when those silicate melt inclusions were trapped could have been a factor as well. But silicate melt inclusions don't only trap the host lithology compositions, as shown from a few of the other diagrams. So we don't know exactly what controls these differences in compositions, but those could be possible factors.
Just to follow up on that, Mark, it's about 20%, 25% of the data shows these really high lead values. And I was looking through the partition coefficient data on, just sulfide silicate for this type of magma composition. And it is a bit puzzling that lead is really coming out higher than the others. But I think we need to look at the actual composition of sulfide inclusions, and we suspect we have some, and see what their compositions are like. And if they're lead dominated, this may explain, maybe lead is being sequestered into a sulphide, and it's just being accidentally trapped, but it's ultimately then being depleted in the end product volcanic rock that is the unit that gets leached. But I don't have a good answer either.
All right. Well, thanks everyone.